Good morning. Welcome. Well, I hope it's morning when you're looking at this. In today's episode, we will be looking at the second effect of forces as stated in our syllabus. Now, the first effect of forces that we looked at a few weeks back was deformation, and that was when a force caused a change in an object's shape or size. Its physical dimensions, basically. Today, we will be looking at how forces affect rotation. Now, this ruler will be my assistant today, and we will look at how its weight and added weights affect how it rotates. So today, our episode is forces, moment of force, rotation, and the principle of moments. Welcome to CSEC Physics with me, Marvin Lee. As said in the introduction, today is the continuation of us looking at the effects of forces, and we will look at our ruler later. In a quick recap of what we did previously, we looked at how forces affect the physical dimensions of an object, for example, the length of a spring. And we looked at Hooke's law, and Hooke's law did state that applied force is directly proportional to the extension obtained. Now, today we will be looking at force causing a different sort of effect, a turning effect. Forces tend to do two things. Well, I shouldn't say just two. Forces can do a few things when it comes to objects and moving them. Forces can move an object from point A to point B, and we call that translational motion. You move it from over here to over here. And then forces can act on objects, like my assistant today, this ruler. And forces can cause this object to rotate. Now, forces actually cause rotation more often than you think. The vibration from your cell phone is actually caused by a small cylinder in your cell phone spinning at a large rate. Now, the cylinder has a small portion missing, and that causes it to wobble, and that's the vibration you feel in your Xbox controllers, your PlayStation controllers. It's the same thing. Fans, any form of motor, tools, chainsaws, cars, planes, anything that rotates actually rotates as a result of the application of a force. Now, forces cause rotation in primarily two directions, as I did right over here. Forces cause rotation in two directions. For simplicity's sake, we always assume we are looking at the object that is rotating from the front. Now, this gives us two directions of rotation. It gives us clockwise and anti-clockwise. Now, I hope I'm going to get this right. Hold on, let me turn just so I can get it right. Clockwise is going to be this way. Yes, I was right. Clockwise is going to be this way. Okay? I pray I'm doing this correct, because this is going to be so embarrassing. My students will never forgive me for this. All right? Clockwise is this way. Now, clockwise, as the name suggests, means that the object rotates like the arms of the clock. All right? Anti-clockwise. Anti-clockwise is the opposite. Anti-clockwise, I do believe, would be this. Okay, this is anti-clockwise. Now, you might be thinking, but we're looking at force and we're looking at rotation. Why are we considering clockwise or anti-clockwise? The direction in which a force acts, if we're moving along a straight line, is important. Okay, if two forces are acting in the same direction, we add them because their overall effect would be to enhance each other. If they're acting in opposite directions along a straight line, they will tend to diminish each other, or the effect each other would have. Same thing applies for rotation. If forces apply to cause rotation in one direction, we have to add their effect. And if forces apply to cause rotation in opposite directions, we have to subtract their effect, or their moment of force. This means direction is important. So please do remember, the directions of rotation are simply clockwise or anti-clockwise, because you're viewing whatever is rotating from in front. You're not looking down on the object or looking at it from the side. You're looking at it from directly in front. So you can see whether it's rotating like the arms of a clock or not. Do remember that. Now, bearing in mind that we have our clockwise or anti-clockwise directions of rotation, we have to move on to this. Now, in physics, almost everything has at least in this syllabus, almost every topic has a formula associated with it. And the formula we're looking at today is the formula for moment of a force. Now, the formula states that T, moment of force or turning effect, is equal to force multiplied by perpendicular distance from pivot. This is important as you probably go on to CAPE and higher levels of physics, but for now, most of the examples that we look at will not require any other direction except a perpendicular direction, or will not ask you to examine cases where the force is not applied at right angles to the object. So don't worry about that too much. So its turning effect again is equal to force by distance, perpendicular distance from the pivot. Now the distance is essentially the distance between where the force acts to where the object is pivoted, all right? Where the force acts to where the object is pivoted, and that is the distance we use. And again, please bear in mind, you have units to consider. Force is in newtons and distance is in meters. So the units for moment of force or turning effect would be Newton meters. Now, this brings us to final point before we move on to something else. What exactly is moment of force? Now, the moment of force is simply the rotation or the effect produced when a force acts on an object which is pivoted and can freely rotate about the pivot. Let me go that over again. The moment of a force is basically the effect a force has on an object which is pivoted and can freely rotate about that pivot. Now, the effect, as you probably have figured out, is rotation. And that rotation will have a direction, and it will also have units. So on we go to the principle of moments. Now, I'm sure you've done this before, and I'll give you a diagram shortly. But imagine this being, let's say this is a seesaw. This is a seesaw, and we have two people. I'm sure you probably, if you've ever had fun on a seesaw, you realize that two people of different masses can sit on a seesaw, and that seesaw be balanced. The only thing is, they can't sit the same distance from the pivot. So if this is the pivot and we have one person who is 2 times the mass of another, they can't sit at exactly the same distances. They cannot. Okay? They can't. And I'm sure you've probably realized that you have to move either closer to the pivot or further from the pivot, and you've worked this out on your own and you've balanced the seesaw perfectly. You know, both of you sitting with your legs dangling above the ground. That is an application of the principle of moments, because what you have done is you have found the position in which the seesaw remains in equilibrium. Now, outside of being a really cool movie, and I do recommend it, Christian Bale was really good in that movie. Equilibrium is great. Go watch it with friends. Equilibrium, actually, you know what? We're social distancing. Don't look at it with friends. Tell friends to look at it in their own time. But equilibrium is simply the state in which we have no rotation, very simply put. So if I just put my hand here, if I just press down, my handmade seesaw will rotate. All right? It will rotate. However, if I don't apply any force here, and I don't apply any force here, and I basically pinch my ruler perfectly in the middle, there will be no rotation. The system is in equilibrium, because essentially the effect of the forces acting on this serves to cancel each other out. So there is no rotation, there is no translation, it's not moving anywhere. I'm holding it and it is simply still. However, if I put my hand on this end, I would have to balance it. Or sorry, in order to balance it, I'd have to press down on that end, which is a bit impossible, seeing I only have 2 arms. I probably should have had 4 arms for this episode. But anyways, if I press down here, that end goes up. And the opposite happens. If I press down on this end, that other end goes up. So what happens is, to balance this rule, if I apply a downward force here, I'd have to apply a downward force on this side, or probably even on this side. Yes, all of that is possible to cause the system to not rotate. And equilibrium is simply the state in which the ruler is neither rotating nor is it moving up and down. There is no motion at all. The ruler is perfectly still. It's not spinning and it's not going up or down. Equilibrium. So the principle of moment simply states that for a system to be in equilibrium or balance, the sum of moments in a clockwise direction has to be equal to the sum of moments in an anti-clockwise direction, about the same fixed point or about the same pivot. So the rotation I cause by pressing down here has to be the same as the rotation I caused by pressing down here, as long as my pivot is maintained, for the system to not rotate. Think about it for a while. Makes sense. That is basically the principle of moments. The sum of clockwise moments is equal to the sum of anti-clockwise moments about the same fixed point for any system that is to be balanced or in equilibrium. I hope you got that. Time for some problems now. This is the principle of moments in words, just in case you didn't follow me speaking just now, and I hope I have them all right. The sum of clockwise moments is equal to the sum of anti-clockwise moments about the same fixed point. And this is the condition for rotational equilibrium, okay? Rotational equilibrium. If this happens, the object, the system will not do the whole rotating thingy, okay? If the moments are equal, okay? If they're equal to each other. Now, this is a formula, and this is how I write it. Sigma is using maths to indicate the sum of clockwise moments is equal to the sum of anti-clockwise moments, and I use T for moment, just like in our formula where I had T for moment of force. Now again, please remember that this is for rotational equilibrium, okay? Rotational equilibrium. Now, the reason this is important, the same fixed point or the same pivot, is if you change the location of the pivot, you actually change the moment produced. So you can't move the pivot around and expect to have rotational equilibrium. The pivot has to be in one spot, and because the pivot is in one spot, this principle will apply. I hope you got that, because right now, me and my ruler friend and a piece of chalk are going to work some problems. I hope you can keep up. Let's go. Now, assuming this ruler is our object, or seesaw, if we put our pivot here at our 50 centimeter mark, and there's a downward force here, all right? Let's call this force 10 newtons. And let us say that this force is, you see, my line ain't even straight. Let's say 0.3 meters from the pivot. Two things have to happen. First of all, if I ask you to find a moment of force, you have to do some calculation. But you also have to include the direction of rotation. Now, I use my ruler for a reason. It's just easy to demonstrate with. If I pivot my ruler here with my fingers and I press down, my ruler rotates like this. For those of you who are puzzled, the hands of the clock rotate like this. So this direction of rotation is clockwise. All right, putting my ruler back. Again, force, distance, direction of rotation. Now, using the formula T, turning effect or moment of force, is force by distance. I have 10 newtons by 0.3 meters. And I get 3 Newton meters. And my direction is clockwise. And that is my answer. The moment of force has to have a magnitude, how large the moment is, and it also must have a direction. Okay? Nothing complicated. So, trust your ruler and I. Now, let's assume, and this is totally possible, we have more than one force acting on my ruler. More than one force. If I have a force acting somewhere over here, and let's say this is 8 newtons, and this distance is 0.4 meters. If I am to find the direction of rotation, you could do this with a pen, you could do this with a pencil, you could even do this with a ruler. Place the ruler on your diagram and just push in the direction, hold the ruler at its pivot before I forget that point, and push in the direction of rotation, or in the direction in which the force acts, and you get the direction of rotation. This would be anti-clockwise. Anti-clockwise. Now, we have two forces acting, producing two different moments. This moment is clockwise, and this one, as we just indicated, is anti-clockwise. Calculating its magnitude, using our formula, we have 8 newtons, 0.4 meters. And I do believe our answer is 3.2 Newton meters. But this is anti-clockwise. Now, what happens here is fairly simple. We have a resultant moment. Yes, I said resultant moment produced. Now, when these two forces act, moments act on the object, there will be rotation because they are not equal. Again, if we go back to the principle of moments, it says the clockwise moments have to be equal to the anti-clockwise moments. And if we look at these two, they are not equal. This is slightly larger than this. If we did the math, it would be 3.2 minus 3.0, which is 0.2 Newton meters. And in physics, the largest force, the largest moment will win in this case. So the object will rotate anti-clockwise. Now you might be thinking, why teach the principle of moments and then give an example like this? I give an example like this because I want you to be aware of the fact that not all scenarios, or in all scenarios, you don't have clockwise and anti-clockwise moments being equal. You can have a case where, like this, they are not. Okay? Because again, there's no rule that says, rather, all clockwise moments and anti-clockwise moments must be equal. This rule, the principle of moments, governs the case where they are equal. But that doesn't mean that's the only case that can exist. Understood? I hope so. Now, another thing you need to note before I forget and before I move on is that looking at the distances on our diagram, these diagrams do not have to be drawn to scale. When you see a question like this, these are not scale diagrams. So I could make this length far longer than this, and I could still call this 0.3 because the length of the line on the page does not actually represent a real distance. Okay? So please remember that these are not scale diagrams. These diagrams are not drawn to scale. So don't assume what the distances are based on the length of the lines. Just don't do that. Okay? So, time for some more problems. Having looked at the principle of moments and the directions of rotation clockwise or anti-clockwise, we need to examine uniform objects and their weight. Yes, uniform objects and their weight. Now, this ruler is constructed or should be constructed to be uniform. Should be constructed. That means if I cut it into 50 equal lengths, each length will have the same amount of mass. Now, mass is the amount of substance an object contains, as we did say in a previous episode. And mass has weight as a result of the action of gravity. So because this ruler has mass, it then has weight. And even if I don't add masses to this, this can still rotate on its own. Let me show you. So if I pinch it at the 50 cm mark, okay, pinching it here, it does a fairly good job of being balanced either side, except for the fact that my hand is moving. However, if I move to the 60 cm mark and I attempt to pinch the same ruler, providing a pivot, we get downward rotation. Why? The center of gravity is here. Center of gravity is here, and there is a downward force exerted because the center of gravity of an object is the point through or at which its weight acts. So if the center of gravity is here and I am pivoting it here, when I let go or when I remove this supporting force exerted by my finger, the object will rotate because its weight is what causes that rotation. Its weight is the downward force. The further I go from the pivot, I moved from 10 cm, I'm now 30 cm away from the pivot. If I remove the downward force, you're going to see that there is an increased rate of rotation. Yeah, that happened. I didn't expect it, but it hit the table. I know, I should have thought it through. But as I was saying, as I increase the distance, the rate of rotation increases as well. Because again, if you think back to the formula, moment of force is force times distance, force by distance. And increasing the distance, I increase the moment of force, or I increase the rotation of the object, essentially. So we can have examples where we have something like this, a uniform object, and its weight is what causes rotation without the addition of added masses. So we're about to look at a few of those examples. Grab your calculators and a sheet of paper and a pencil, because you might need to double check my work. You never know. I have assembled 3 problems, 3 very different problems that are just to be used to bring out a few important points when it comes to moment of force. So in our first example, we have, I wrote the data in a very, very abbreviated form. A plank of length 6 meters and mass 10 kilograms. Now, for the sake of ease of understanding, and I also know that it removes a lot of problems and difficulties, all the planks here are pieces of wood are assumed to be uniform. Right? We assume they're uniform. That means mass is evenly distributed throughout their length, and that means their weight would act through their geometric center. Okay, remember, uniform, weight acts through geometric center. For the first one, I gave you mass. Now, mass is 10 kilograms. If you remember, there is this little formula. A little formula that says this. Weight is equal to mass by acceleration due to gravity. W is equal to m times g. Mass is 10. And let's take acceleration due to gravity as 10 meters per second squared, or 10 newtons per kilogram. So we have 10 by 10, and this gives us a grand total of 100 newtons. Now you might be thinking, what does that mean? That means the weight of this 6 meter long plank is 100 newtons. That means the weight is going to act downwards somewhere from the middle, and the value of weight is 100 newtons. So middle of a 6 meter plank would mean that this distance is 3 meters. So we converted mass to weight, we put it in on our diagram, and we put our distance in. Now, why is this important? Many times you'd find that the problem is written, the problem will not be drawn, and you have to draw a diagram to help you represent the information, and you have to put in the magnitude of your forces, the position at where they act, and also the distance from the pivot. Please note that I put in my force, I put in my distance. So let's assume the question asked, calculate the moment of force this produced. Calculate the moment of force. Again, our formula is moment of force is force by distance. Our force is 100 newtons, and our distance is, from our diagram, 3 meters. Again, let me go over why. The plank is 6 meters long and uniform. That would mean that its center of gravity is exactly in the middle, and the middle of 6 is 3. So 100 by 3 is 300 Newton meters. And our direction of rotation would be this way. How do I know? My friend, if I use my ruler, it's a bit too long, and this is my pivot. Well, I could put it like this, and this is my pivot, and I push down here, my ruler will move in a clockwise direction. So my direction of rotation is clockwise, so my moment is clockwise. And that's it. Very simple. Very, very simple. Now, on to the next one. So in my second example, I have a plank supported at two ends. Supported, not suspended, and I'm trying to show you that. So I have my two plastic cups, and so basically this is what we have. Now, supports at the two ends, uniform plank, the weight would be in the middle. It should be somewhere around here. somewhere around here. Now, this is a scenario, right, in which you might be thinking, but there are two unknown forces. Oh my goodness, what do we do? You can find the two unknowns. You honestly can. Now, again, the basics are stated. I said the plank is 4 meters long and its mass is 20 kilograms. Again, for this level, the plank is uniform, which means if it's uniform, it's 4 meters long, so somewhere in the middle, we have its weight. And weight is mass by acceleration due to gravity. We take acceleration due to gravity for ease of calculation as 10. So it's basically 20 times 10, and that is a whole 200 newtons. So our weight is 200 newtons. Now you might be thinking, but sir, we only got one force and we got two unknowns. The good thing is this: you can use a little trickeration to find either F1 or F2. So let's try to find F1 first. Now, let me ask a simple question. The formula for moment of force is T is F by D. So if D is 0, what is T? The surprise answer is that T is 0 as well, because it doesn't matter what the value of force is. If this is 0, 6 trillion by 0, last I checked, is still 0. So what we can do, all right, is we can make here a pivot. Why is that important? Pause this video, go to your door, go to your gate, if you have a swinging door or swinging gate, and push the hinge. Apply pressure on the hinge. I never said push the door or the gate off the hinge. I said apply pressure to the hinge. Now, I don't know if, anyways, you could pause. I don't need to stand here and wait. If you push the hinge on a door or a gate, what you will find is that the door or the gate shouldn't move. If your door or gate does move, that's a bit unscientific. But if you're pressing on the hinge of the door or the gate, it shouldn't swing. The door or hinge, the door should stay, or gate rather, should stay where it is. If you push on the hinge and your door swings closed or moves, might be, you know, something a little wrong with your door. Because again, by the principle of, not the principle of moment, sorry, by the formula, if the distance of force acts from the pivot is 0. Now, let me explain this really closely. The only way distance from pivot is 0 is if the force is acting on or at the pivot. If you're pushing on the door hinge, the force you apply is on the pivot. The hinge is the pivot. So the door shouldn't swing, the gate shouldn't swing. If I make this the pivot and this force is acting on the pivot, it means that this force, F2 produces no moment, it produces no rotation. So I now essentially, for all intents and purposes, and please do forgive the condition of my eraser, I just get rid of this. If that is now the pivot, this does not exist. It doesn't exist. Now, why it doesn't exist? It doesn't exist because I've made it the pivot. And by making it the pivot, it produces no moment. Go it over again. If D is 0, T is 0. D 0, T 0. Remember that, please. Now, what it means is that I only have two forces, this and this. The assumption you'd have to make is that this system is in E-word, equilibrium, equilibrium. And if it's in equilibrium, your clockwise rotational moments be equal to your anti-clockwise moments. So again, with the help of my trusty friend, let me put it this way so you can see the 50. If this is our pivot, not our pivot, sorry, if this is our weight, if this is our pivot here, this force, I think that's clockwise. Correct me if I'm wrong. but it is. And this one, with the pivot here, this is anti-clockwise. Okay, anti-clockwise. So, working it out, clockwise we have force by distance. Now hold on, wait. Pivot here, force all the way over here. The distance is our length because the force is acting at one end, the pivot is at the other, and our length is 4. So it's F1 by 4 meters. And anti-clockwise, we have force by distance. The plank is uniform, so the weight acts in the middle, and the middle for anything that long would be 2. So it's 200 by 2. How did I get 2? I just divided this by 2 and divided it in half because it's in the middle, and the middle means equal lengths on either side. And again, by the principle of moments, these two are equal. Your clockwise is equal to your anti-clockwise because you're in equilibrium. So F1 is 400, 200 by 2 is 400, divided by 4. F1 is 100 newtons. Again, how did we do this? We made the pivot one end, removing the force that was acting here, which is F2 from the equation. Why did we remove F2? Because since this is the pivot and F2 acts on the pivot or at the pivot, the distance from the pivot became 0. With the distance being 0, there was no moment of force, and therefore we could have said this and this are in equilibrium, and we found that. So, some homework. I know. I'm giving you homework. Do the same thing to find F2. Make this point the pivot and repeat the whole process, because if this is the pivot, F2 doesn't produce any rotation. Sorry, F1 doesn't produce any rotation if this is the pivot. Again, do the same thing that you did here over here. Make this point the new pivot. F1 therefore produces no rotation, so we have weight and F2. And then you can simply find F2. My bet is F2 is 100 newtons. Why is F2 100 newtons? Small trick. If you look at these forces, we have two forces acting upwards, 1, 2. We have one force acting down. The total upward force has to be equal to the total downward force. So, if the total downward force is 200 and F1 is 100, the only other force we can add to this 100 to get 200 is another 100. Remember that too. Total upward force equal total downward force. Just in case. Now, that's my second example. It's time for the third. All right, so for the final one, this one, okay? You might be thinking, but why all these examples look different? One of the cool things about this topic is that you can create so many different examples. All right, there's so many different scenarios that can be found. And what you have to remember is that the basic rules apply. Moment of force is still force by distance, ever, only, and always. And the principal moment states that for a system in equilibrium, the sum of clockwise moments is equal to the sum of anti-clockwise moments. Like, that's it. You remember those two things and you're going to be fine. So, here we see one force is 6 newtons. Yes. One force is 8 newtons, and then one force is A. Yeah, you have to find A. How do we do this? Again, always start with figuring out, like, how does this force cause this system to rotate? So, let's see if I can put, yes, pivot. Green force, 6 newtons, acting from the bottom up. But you look at that. I do believe this is anti-clockwise. And then over here, acting down, I do believe this is clockwise. And again, I do believe this is clockwise as well. So now we have two forces acting in the clockwise direction and one acting in the anti-clockwise direction. I just said something really wrong. I said forces. I should have said forces producing moments in the clockwise direction and force producing a moment in the anti-clockwise direction. Forgive me for my sin, O gods of physics. So, moving on. Again, if we look at the clockwise direction, it's force by the corresponding distance, 1. 8 by 1 is 8 Newton meters. Now, I have already indicated my direction up here, so I don't need to put clockwise next to it. And again, for the second force, it's force by distance. So, what's the distance? The distance is actually not this, nor is the distance this. The distance is this plus this. Why? Because if we look at how far this force is from the pivot, you'd see that it is this distance. The force is here from the pivot, not here. Every time this question or questions like this are given, students tend to forget that it's not the distance from the nearest force, it's the distance from the pivot, which is this plus that, because the pivot is here. So it's not 0.5, it's not 1, it's actually 1.5. Now, how do I set this out? I simply put the name of the force, I call it A, by the distance. And if you're doing algebra, you just get 1.5 times A. That's it. Anti-clockwise, we just have one thing. We have force by distance, and 6 2s be 12. 12 Newton meters anti-clockwise. So let me write that. So anti-clockwise is force by distance. So by the principle of moments, the sum of these two is equal to this, not 1. This plus this is that. So if I had to write it out, it would be 8 plus 1.5, A is equal to 12. I know I left units out. I'm running out of space. That's why. Now, 1.5 A is 12 minus 8, which is 4. A is equal to 4 divided by 1.5. 2.67, I believe. Let's see, 3 upon 2. I'm just going to do it by fractions. 3 upon 2, 4, yeah, 2.67. 2.67 newtons. Again, we did this because we remember two things. This force is this distance from the pivot, and if this system is in equilibrium, your clockwise moments would be equal to your anti-clockwise moments. So, that's it for today. Please remember, moment of force is the effect force has on an object which is pivoted and can freely rotate about the pivot, because when a force acts on such an object, rotation happens. An object which is uniform has basically the same mass throughout its length, same mass distribution. And the principle of moment states that the sum of clockwise moments is equal to the sum of anti-clockwise moments about the same fixed point or pivot. So, I hope you got your examples right. I hope you remember my homework for number 2, and I hope you have a good day. I will see you on the next episode of CSEC Physics with me, Marvin Lee. Peace.